Let's talk about rational functions. First off, let me define a rational function. Rational function, I'll call it r of x, is equal to the ratio of two polynomial functions, or one polynomial function over another polynomial function. P of x and q of x are both polynomial functions. Now, if we think about a polynomial, we knew a lot of different things about polynomials. We could find its x and y intercepts. We could find whether it was going to be what the end behavior was going to be doing, what the ends, which directions they were going. We could know how many times it was going to turn or how many x-intercepts we were going to get based on that polynomial. So we knew quite a bit about these already. So if we're taking this and simply finding their ratio, there's going to be obviously some things that are different, but there should also be some things that are kind of the same. And so we're going to study those things. To give you a very basic idea of the most basic rational function, 1 over x, I'm going to go ahead and give you what this graph looks like. Graph of 1 over x has this shape to it right here. So there's some different elements to this rational function, and I should point out too that this is one rational function. Rational functions take on a variety of appearances. Okay, this right here can be given to us through a rational function, very different looking than the previous example. We could see that we have multiple places where the function is seeming to jump around. But if we take this function 1 over x and think about it, we see that there is a domain restriction at 0. We never have the value x is equal to 0, and that should make a lot of sense based on the x in the denominator. We now have a denominator. So we can see that 1 is just a polynomial function, x is a polynomial function, but because we have their ratio, because we're dividing the two, x is in the denominator, we now have a problem anytime the denominator is equal to 0. That gives us this thing right here, where one side is shooting up to infinity, one side is going down to a negative infinity. This thing that we are approaching is very special. That is something called an asymptote. And in this case, it is a vertical asymptote. Now, you may have heard a definition of an asymptote before, and I want to make sure we're all on the same page. I've heard the definition before. Asymptotes are imaginary lines that you get close to, but you never cross. And that is false. We can cross asymptotes. So a better definition of an asymptote for this point, it is an imaginary line that we will approach or that we get really, really close to. And we see that that is true not only in the case of the vertical, where we said we can't actually have 0, but we see these ends are getting really, really close to it. But it is also true of these two ends, where they're getting really, really close to this horizontal line. That would be a horizontal asymptote. We can cross horizontal asymptotes. Vertical asymptotes you won't cross. That one is true. But horizontal asymptotes can be crossed, and so we want to be careful saying that we can't cross them. We can. Now, I showed you a couple other pictures too. Notice this one I said is a rational function. It doesn't actually have any asymptotes. It has this thing right here. It has this removed value as a whole. And depending on where that hole is, we could, if I define it to say be the value of 1, maybe this equation is the function g of x equal to x minus 1, and then on the top we could have x minus 1 times x. And this rational equation would give us this graph right here. It looks like a straight line, x, except for there's that value of 1 removed because it's a hole, and we'll talk about why that's a hole, how I know that that would work. And then we have this last function here. This one would be a more complex version of both of these. There would be multiple pieces in both the top and the bottom that would cause this shape to happen. And so we're going to see how all these things come about. But rational functions, we might have some holes, we might have some asymptotes, we might have a combination of the two. And so let's figure out when we have each thing. We're going to start with the vertical asymptotes. And I always say vertical asymptotes slash holes. Now, I'm always going to abbreviate vertical asymptotes to VAs just to make my life a little bit easier. Vertical asymptotes VA, and then holes just right out. So the way that we find both of these things, if we think about what we said they were up here, it's when we have that 0 in the denominator, and that's obviously what we're not allowed to have. So we're going to set the denominator equal to 0. Whatever we get from that is going to be a hole or an asymptote. And so then the question is, how do we know which one is which? And there we have to look at the factors of the polynomial of the numerator and the factors of the denominator. Factor top and bottom. Factors of the top or of the numerator, but not the and the bottom, yield wholes. If a factor is unique to the denominator or to the bottom, that yields a vertical asymptote. So really, I kind of write these out of order. What we are doing is we are setting that denominator equal to 0, but it does help just to go ahead and factor top and bottom first. Because if I can see what those factors are, then I can set the denominator equal to 0, in both cases solve them, but I'll know whether they're going to be wholes or vertical asymptotes. So let's do an example. Let's say we have the function x minus 1 over x plus 3. This is very basic. So if I look at this thing, I'd say, well, clearly it's already factored, so that's done for me. X minus 1 is not the same factor as x plus 3. So I'm going to go ahead and set this equal to 0, but all the while, I know already this is going to be a vertical asymptote and not a whole, because those factors are not the same. So I get x is equal to negative 3. And that is my vertical asymptote. Notice, too, that it is an equation, because we said these are vertical lines. They're imaginary vertical lines, but they're vertical lines. And so a vertical line always has the equation x is equal to. Let's take another one. Let's say we have g of x is equal to x plus 3 times x minus 2 over x minus 2 times x plus 1. Well, again, the hard work's been done for me. It's already factored. So I can see very clearly that 2 of the factors match and then 2 of them don't. So the ones that match, I know will give me a whole. There will be a whole when I set x minus 2 equal to 0. The one that is unique will give me a vertical asymptote, the x plus 1. Why am I not setting the x plus 3 equal to 0? Well, we don't care when the numerator is equal to 0. That is not a domain restriction. So think, we've already done this before. When we're looking for the domain of polynomials, we set the denominator equal to 0 and we solved. But before we didn't name them, now we're going the extra step and saying, hey, we know that this doesn't exist in the domain, and we also know now why. It's either a whole or a vertical asymptote. So if I solve the first one, I get x is equal to 2. That is my whole. And then if I solve the second one, x is equal to negative 1, that is my vertical asymptote. Now, polynomials won't always be so easy. They might be multiplied out. So let's say we had this polynomial. Well, I can't see by looking at it which factors and which ones match and which ones don't, so I better start by factoring. And I have my factors x and x, then 2 would be 2 and 1, and then I'm going to need, because it's a plus 2, I need negatives on both of those. That would give me the negative 3, so that factors. The denominator, I'm going to start with my x and x, but this time because I have a minus 6, my factors have to be a plus and a minus. Factors of 6 are 1 and 6 and 2 and 3. Because the signs are different, I have to use the 6 and the 1. So once we have it factored, well then I set the factors equal to 0. But I'm going to go ahead and think about, are they going to be wholes or vertical asymptotes? Well, the 6, x plus 6 is unique. That one's going to be a vertical asymptote. While the x minus 1 is the same on top and bottom. So that's going to give us a whole. So here I've done 2 examples. Forgot to write this was a whole. 2 examples where we have one vertical asymptote, one whole. I've done one where we just have a vertical asymptote. And remember, something like this one up here can give us just a whole, because notice those factors top and bottom match. We get a whole of 1 and then nothing else. There's no other vertical asymptotes. So it is completely possible that we have a vertical asymptote and a whole. It's possible that we have multiple vertical asymptotes and wholes. We could have 3 and 2, or 7 and 1, or 9 and 0. So it's any mixture thereof. How do we know? Well, the degree of the denominator will give us the largest number possible. So here our degree was 2. We knew at most there had to be 2 wholes or vertical asymptotes. Can't be 2 of each, but 2 in total. Here our degree was also 2 in total. Here our degree was only 1. So if we saw something where we maybe had g of x is equal to x to the, I don't even care what it's in the numerator, but if I see in the denominator x to the 9th plus blah, 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 whatever else is down there, I know at most 9 vertical asymptotes or holes. In total, there would be 9. Now, that's not to say that the polynomial gives us the exact number. So let's say we had 1 over x squared plus 1. Well, here, let's set that denominator equal to 0. Clearly, the factors don't match on left and right. Let's set it equal to 0. I move my 1 over. I take my square root, and I get a plus and minus. Well, those are imaginary numbers. There's no vertical asymptote nor hole because those imaginary numbers just don't play a part in my x and y axis. So here would be an example where we see a degree of 2, yet there are no vertical asymptotes nor holes whatsoever. Let's move on to horizontal asymptotes. Now, I've done a very hand-wavy definition of an asymptote. I said that it is something that we approach. We can cross, we might not, but it is this thing that we approach. What this approach is really talking about, it is something called a limit. And we haven't defined limits in this class, and we aren't going to define limits. You talk about those in calculus, but a limit's there's a little bit more going on to this. And so if we think about those horizontal asymptotes that we defined before, that we saw before in our picture, let's scroll back up. That horizontal asymptote, we saw we're getting really, really close to the x-axis as we went off to infinity. Same thing here on the ends, not so much in the middle. The horizontal asymptotes, we want to look to see what happens as the polynomial, or I should say as a rational function, progresses outwards indefinitely. Where do those ends go? Do they go to 0? Do they go to 1? Where do they go? And so I give you this little bit of a background so we can figure out how to come up or how to generate these rules for the horizontal asymptotes. But I'm going to give you some rules. So let me go ahead and scroll down and we'll set up these rules for horizontal asymptotes. Now there's going to be 3 different cases. Remember how we defined a polynomial rational function, the rational function of x? It's the p of x over the q of x. And so I'm going to reference the numerator and denominator in terms of this p and the q. So the first possibility is that the degree of the denominator is bigger than the degree of the numerator. So let me write that out. The degree of the numerator is less than that of the denominator. If that is true, we have a horizontal asymptote y is equal to 0. And notice that I'm setting it up as an equation again, because it is a horizontal line. Horizontal lines always take the form y is equal to, and then we are just inserting the value that we find it is. We found that it was 0. Why is that the case? Why does this rule exist? Well, remember what we're saying is we're letting those x's go off to infinity. So we can't really plug infinity into a polynomial or into a rational function. But if we think about the denominator being bigger, that means that we're getting to infinity a little bit faster. If we get to infinity a little bit faster, think about 1 over 10, 2 over 100, 3 over a million, 4 over a billion. Well, those numbers are getting closer and closer to 0. Let's look next if the degrees are the same. The degree of p of x is equal to the degree of q of x. In this case, our horizontal asymptote is going to be y is equal to the leading coefficient of p of x over the leading coefficient of q of x. And again, why is this the rule? Well, if the degrees are the same, that means the exponents are causing the infinities to go there more or less the same rate. They're going to be off by the coefficient. And so we'll see examples of these a little bit more in a second, and I'll talk a little bit more through that idea. I'll wait till we get to the example. And then finally, if you haven't figured out what the third one's going to be, the degree of p of x, in case we haven't done, is greater than the degree of the denominator, the q of x. Then there is no horizontal asymptote. So this is always where in class I'd try to trick the class. I'd say, which of these three rules do you want to see on the test? And I almost always get the third case right. It looks like it should be really easy. Horizontal asymptote, not there. The trick is there will be a slant asymptote, which you might also see called an oblique asymptote. So we'll go over those rules too, but let's talk about the horizontals for a minute first. So let's say we have the function 8x plus 3 over 2x squared minus 1. I'm just going to worry about the horizontal asymptotes for right now. So if I look at this thing, I see the degree of the denominator is bigger than the numerator, which tells me right away y equals 0. If I were to try and think about this thing as going off to infinity, I can't plug infinity, but I can think about that idea. This thing is going to infinity much quicker than this is, which is driving the whole fraction to 0. Let's take g of x is equal to 8x squared minus 2x plus 1 over 3 plus 5x squared plus 2. Tried to trick you on this one by listing them out of order, but if we look for the degree at the top and the bottom, they are both 2, even though it's not written in descending order. And so according to my rules, the horizontal asymptote needs to be the leading coefficients. My leading coefficient of the numerator is 8. Leading coefficient of the denominator is 5. Remember, it's not necessarily the first thing. It is whatever is attached to that largest exponent. So our horizontal asymptote would be 8/5. This is the rule that I kind of glossed over earlier. If we think about both of these things going to infinity, the plus 1, the plus 2, plus 3 really just don't matter. The thing that is driving this thing to infinity the fastest is that x squared and the x squared down there. So they're the driving terms, but obviously they're not quite the same because the one has an 8 in front of it, the bottom one has a 5 in front of it, and so that's where we're getting that 8/5 from. Again, in calculus, we'll go deeper into these rules and really understand how we get to these asymptotes, but I'm going to leave it there for now. Then finally, let's take one last function. Let's take 5x squared plus 2 over x minus 1. This would be an example for which there is no horizontal asymptote. The numerator is growing faster than the denominator here, so this thing is growing out of control. However, I did say that there would be a slant asymptote or an oblique asymptote. I should also note that that is only true if the degree of the numerator is 1 greater than the degree of the denominator, which those are the only types I'm going to be giving you in this class. Again, in calculus, that's where all the fun stuff happens, so carry on to calculus. But in calculus, you would learn a little bit more about that still. But for right now, let's talk about those slant asymptotes. To find the slant asymptote, divide the polynomials and drop the remainder. So now that we know that this thing has no slant asymptote, let's go back and let's find its slant asymptote. I need to divide these two things. Well, the easiest way now to divide polynomials is using my synthetic division, that it only works if the degree of the denominator is 1 and the coefficient is 1. That is all true. So I can use my synthetic division. I'd have a plus 1. I switch my sign. My coefficients are 5, 0, and 2. Bring down my 5, bring up my 5, bring down my 5, bring up my 5, bring down a 7. But that 7, remember, is the remainder, so I drop it. And so my slant asymptote would be the equation y is equal to 5x plus 5. And so no horizontal asymptote, but there is one slant asymptote. There will only ever be one horizontal or one slant asymptote. We will not have both. So we will only have one or the other. We will not have both. We will not have more than one. Vertical asymptotes and holes we can have any number of based on that degree of the denominator. Horizontals and slants, only the one. Now, this was an example where I could use synthetic division. Let's just real quickly take a look at an example where we couldn't. So let's take 5x cubed minus 2x squared plus 5x plus 4. Let's divide that by x squared plus 1. Well, now we have a polynomial that's no longer of just degree 1, so I'm going to have to use my long division. X squared plus 1 is going to go on the outside. 5x cubed minus 2x squared plus 5x plus the 4 is going to go on the inside. What times x squared gives me 5x cubed? Well, 5x. 5x cubed, and then 5x times 1 is 5x. Next thing I'm going to do is subtract. My negative 2x squared comes down. 5x's are gone. I can bring down my 4. What times x squared gives me a negative 2x? Negative 2. And so I get a negative 2x squared. That would be a minus 2. I don't really care because everything else past this point is going to give me the remainder. Notice here I'm just left with the constant, so the next thing coming is the remainder. I would have a remainder of 6. I don't care, like I said, I don't care about that. Once I see that that's zeroing out, that is going to give me that slant asymptote. So for this problem, I know that I would get the slant asymptote of y equals 5x minus 2. In the next video, I'm going to put this all together and actually graph the rational function. So we will be finding x and y intercepts in the next video.